So slightly simpler things today than last time. Introduction into what magnetic resonance is for the people who have grown up in physics and mathematics departments and have not been exposed to magnetic resonance in your laboratory practicals. Of course, chemists would be closely familiar with what I'm going to say today, because from your second year organic chemistry you have had to run NMR spectra on everything you synthesize before you hand it in to your demonstrator. Okay, so what is NMR spectroscopy? Why is it important? And what are the principal considerations that we have to take a look at before we proceed to the actual methodology, data analysis, computational modeling, and such things? Well, the summary of the previous two lectures, as I told you then, nuclear spin isn't actually spin in the same sense as electron spin. It is the total angular momentum of the ground state of the nucleus at the energies that chemists would realistically access. We do not populate nuclear excited states, and so for us nuclear spin is fixed and more or less a fundamental constant. If you have a nucleus of spin s, it would have 2s plus 1 energy levels. You all know that from your basic courses. And there are, broadly speaking, three types of nuclei out there. There are spherical nuclei with 0 spin, like carbon-12 and oxygen-16. They are not NMR active because they don't have a magnetic moment. There are spherical nuclei with spin half, and these are the most popular magnetic resonance nuclei, like carbon-13 and nitrogen-15. Phosphorus if you are into nucleic acids and catalysts and so on. And there are non-spherical nuclei, which, because they're non-spherical, have an electric quadrupole moment, and we discussed it in the previous lecture. The direction of the nuclear electric quadrupole is aligned with the direction of the spin, and this significantly complicates magnetic resonance spectroscopy on these nuclei, unless you are specifically doing materials, catalysis, energy storage, and so on. You probably want to avoid them, and if you are doing batteries, then tough luck, folks. Lithium's your best friend, and it's the quadrupolar nucleus. So hard to observe. Magnetogyric ratio, we derived it in broad outlines in the previous lecture. Electrodynamics requires charged spins to have magnetic moments. This is where it comes from. And the magnetic moment of a nucleus is proportional to its spin. That is to say, if we have a vector of the nuclear spin as an observable, there is a proportionality coefficient, I showed you in the previous lecture where it comes from, that relates the spin to the magnetic moment. And because a magnetic dipole, when you put it into a magnetic field, acquires an additional energy depending on the relative orientation of these two, we get the energy level splittings. Never forget about this minus here. Even textbooks sometimes miss this. This is the most important minus in magnetic resonance, particularly if you are doing things like dynamic nuclear polarization, because electron magnetogyric ratio has the opposite sign from the proton magnetogyric ratio, and the opposite proton one has the opposite sign from nitrogen-15. So unless you consistently account for these minus signs, a lot of calculations would become incorrect in magnetic resonance. So as we saw yesterday, spin is mathematically similar to orbital angular momentum, but physically distinct. Its symmetry group is SU2, and its algebra, although it's isomorphic to the algebra of orbital angular momentum, it is not identical to it. It is physically distinct. And, well, spectroscopy of spin systems is broadly similar to every other electromagnetic spectroscopy. It all started in the 40s and the 50s, literally a source of electromagnetic radiation, our radio frequencies in typical magnets, being shown through a physical system and at the frequencies that correspond to allowed transitions between energy levels, we are seeing absorption, and this is where the detector sees a decrease in the transmitted power when the source is sweeping through all the frequencies. And this is super informative. This was realized early on. Two chemists, because line position, right, so the shift of this line provides information about the chemical environment, because nuclei are somewhat shielded by the surrounding electrons, and depending on how much electron density you have around and what is the distance to the nearest excited state, you would have the shifts in these lines. These splittings, the fine splittings here, depend on interatomic distances, bond angles and types. Skilled chemists, and you can do that as an experiment, find some complicated molecule on the internet, print its NMR spectrum and give it to your nearest chemist. They will, in 15 minutes, roughly sketch you the molecular structure. We drill them really hard in chemistry departments. They actually memorize these frequencies for different functional groups and different combinations of them, and these splittings for different combinations of atoms and bonds. A skilled chemist can interpret these things just straight away from just staring at it. As you will see in the subsequent lectures, this frequency sweep is no longer how we do magnetic resonance. Now this is Fourier spectroscopy, so you give a hard pulse, record the ring down and Fourier transform it. We will cover it in some detail a few lectures down the line. And reminder to physicists that what we call a spectrum in electromagnetic spectroscopy is Hamiltonian eigenvalue differences, right? So these are energy level splittings there. And that's a typical biological sample that you are dealing with. Ubiquitin protein, a few hundred proton spins, a few hundred carbon-13s if you enrich it with carbon-13, and a bunch of nitrogens. So these are really large spin systems, and believe it or not, every atom in this entire molecule has, with an instrument of sufficiently high resolution, a different frequency and a different splitting pattern. And this is in fact how a significant fraction of the protein structure database has been populated. It was magnetic resonance people getting these structures. Information content is quite extraordinary, and let us start with, well, just the frequencies, right? So when we have a spin that is quantized along the applied magnetic field, what is the frequency of the transition going to be? Well, gamma times the spin is our magnetic moment. It goes into the energy expression, and so that's the minus. The difference between spin up and spin down is exactly 1, so we've got minus gamma bz, and this is the frequency. And typically gammas are tabulated in the literature in radians per second, so natural units that quantum mechanics and spectroscopy operates in. Magnetic fields are in Tesla, and so the units here are radians per second per Tesla, and whenever you see an omega in magnetic resonance literature, this is always angular frequency, right? Never try substituting hertz. This is supposed to be radians per second, so 2 pi times hertz. For hydrogen nuclei in a typical 11.7 Tesla magnet of the kind that your department would have in the basement, that's the magnetogeric frequency of the proton. And then if you divide it by 2 pi to convert it to linear frequency, that's about 500 megahertz. And if you multiply it by the Planck's constant and by the Avogadro's number to get it in joules per mole, you can see this is tiny. This is in millijoules per mole. This is much lower than the chemical energy scale. It is very uncommon for nuclear spin processes to influence chemical reactions in any way. For all intents and purposes, nuclei are just transported by chemical reactions, and nuclear spin doesn't have much of an influence over the reactivity. Because of this, the energy level population difference is tiny. If you take Boltzmann's law and you put this frequency into here, times it by the Planck's constant, divided by the kT and exponentiate, this is the population ratio between the spin down and spin up. And if you work it out, well, by just saying that P down plus P up is equal to 1, and using this as the second equation, you can work out the difference. The difference is of the order of 10 to the minus 4. So the sensitivity of nuclear magnetic resonance is quite low because the population, energy level population difference is quite low. And even 11.7 Tesla, where this happens, can be $500,000 if you are buying the latest electronics with it. So low sensitivity, expensive magnets. That's the first few elements that are popular as reporters in magnetic resonance. Of course, protons, because of high natural abundance and high magnetogyric ratio. Nitrogen 15s are not very abundant, less than 1%. Likewise, carbon 13, just about 1%. Blame the supernova that is responsible for the heavy elements here on Earth. It didn't do a very good job with our isotopes. Phosphorus, thankfully, is 100% natural abundance. Likewise, fluorine, to the approval of a lot of pharmaceuticals people, because significant number of pharmaceutical substances are fluorinated these days. And so what we need to take a good look at now is the physical origin for why nuclei at different chemical locations inside different chemical functional groups would actually have different Larmor frequencies in an NMR magnet. So our mission today is to put some quantum mechanics into place and then have an explanation for why nuclei in different chemical groups would have slightly different frequencies. Firstly, however, we need to take a look at ways of improving sensitivity. Biologists present, those of you who are doing protein NMR spectroscopy, would be very familiar with this. The problem, of course, is there's only 1% and less than 1% natural abundance of C13 and N15. So in principle, what we can just do is take a bucket of bacteria which are expressing our proteins and feed them carbon-13 enriched glucose. That is quite expensive, but they would happily munch the heavy glucose and produce isotopically labeled proteins. And if we feed them N15 labeled urea, that in principle can be used as their only source of nitrogen 15. They would happily synthesize isotopically enriched proteins for us. And then you kill the poor little bacteria and you take their proteins away and you purify them. And this is how a lot of structural biology is done these days with magnetic resonance. If the substance is something that a biological system cannot synthesize, for example a pharmaceutical, we can synthesize them directly from isotopically enriched precursors. In that case, it's not just expensive on the source materials, it also takes a very skilled person a very long time, and so personnel with those kinds of skills is very hard to come by, and so that ends up even more expensive. What we could in principle do is try reduce the sources of noise. There are two sources principally, the noise of electrons in conductors, Johnson-Nyquist noise. We can simply just cool down our preamplifier, our cables, our amplifier, our probe circuitry, everything down with liquid nitrogen, liquid helium, depending on how rich you are, and then this level of noise is dropping. And then, of course, we can cool down our actual sample. For biological samples, this is not very practical, because if you freeze them, they stop working like they normally would. But for some other samples, cryogenic magnetic resonance is an option, because the population difference for nuclear spins is roughly inversely proportional to temperature. It's the sort of temperatures that we would realistically populate. Then we can buy a bigger magnet. And unfortunately, magnets do not evolve very fast. In 1960s, right, we had a Tesla or so. Now we have about 30 Tesla, and slowly they're pushing their way up different types of magnets. The latest you can buy from Bruker is 1.3 gigahertz. And these are one in a country kind of expensive. So I was there at the various committees and application boards when we were buying one of those magnets for the country of the United Kingdom. And it ended up in Warwick, and then the funding agency, EPSRC, phoned up University of Birmingham and said, well, by the way, it's the end of the financial year. We found a few more £1 million behind the sofa. They said, would you like another magnet? And so Birmingham had to chime in and provide some money on its side, but we now have two 1.2 gigahertz magnets in Britain, so at roughly 10 to 20 million pounds each. So these are very expensive toys. Here at Weizmann Institute we have 1 gigahertz, so only slightly below that. And the sensitivity goes as a power of the main magnetic field, but well, it is expensive. And we can use quantum mechanical tricks as well. We can transfer polarization from easily polarizable particles like electrons. We can try and cool systems dynamically by, for example, continuously exchanging spins with the solvent. We can use quantum optimal control to reduce the intermediate losses in complicated experiments. But, well, this is all difficult. What you will constantly see as chemists and physicists when you are working with spins is the blasted low sensitivity. That's unfortunately a fact of life. But that having been said, information content is quite extraordinary. You will have a full explanation for what this is in a few lectures' time. This is a two-dimensional Overhauser effect NMR spectrum. Roughly speaking, the red peaks in here, their position along the diagonal indicates what kind of chemical functional group the spin is sitting in. All the off-diagonal peaks in here are distances, so when the two nuclei are proximate in 3D space, you would have a cross peak, and the volume of this cross peak, if you integrate it, is proportional 1 over r to the 6, where r is the distance between those two spins. If you can analyze this really well, and spectroscopists these days can, it is possible to extract full three-dimensional structures of pretty complicated substances from this within minutes to hours. This is how a lot of pharmaceutical structures, protein structures, nucleic acid structures, ligand binding, and so on, is investigated in chemistry these days. And note that various processes in magnetic resonance are to a significant extent dissipative. If you are doing quantum technology, to you relaxation and decoherence is a nasty enemy to fight. To magnetic resonance people, this is a source of information, because all of these cross peaks in this particular spectroscopy are actually incoherent magnetization transfer. So to us in magnetic resonance, certain types of relaxation are actually valuable sources of information, because we understand those processes so well. Okay, so let us provide a few explanations of where all of this comes from and why you have these line position dependencies and coupling dependencies on the local chemical structure. Well, we need to introduce magnetic field into quantum mechanics. To chemists, certainly, this has not been given in their undergraduate courses. You were given Schrödinger's equation with all the electrostatics in it, but none of the magnetic fields. We start, as ever, with Maxwell's equations, so we treat our E and B classically. And, well, remember, our electric field is the gradient of the electrostatic potential, and then the little term that depends on the time derivative of the vector potential, and B is the curl of that vector potential. This is classical Maxwell's equations. We are not quantizing electromagnetic fields here. When we introduce this into quantum mechanics, well, remember, when an electron flies through a magnetic field, it experiences a Lorentz force, and that is a correction to the momentum term in the Schrödinger equation. If you work through the mathematics of it, you get this correction. If this is the magnetic vector potential, and that's the charge of your particle, then our usual term, momentum squared over 2m, has to be modified to account for the Lorentz force. And the electrostatic potential just remains the same like it was in your usual, hydrogen atom type Schrödinger's equation. So we have the kinetic energy and the potential energy, and so kinetic energy is modified in the presence of the magnetic field. And then the vector potential has two sources. There is the uniform magnetic field that comes from the big magnet, in which the system is sitting. But of course every nucleus is a magnetic dipole, and so they would contribute to the dipolar part of this vector potential in a distance dependent way. There are a few mathematical intricacies here that I will not touch upon because this is a curl. Of course, the curl of any gradient is a zero, and so this vector potential is defined up to a gradient of an arbitrary function, so-called gauge transformation, with the result that there are a few terms in here on which the physics in the end does not depend, but they are internal degrees of freedom of the mathematics itself, the so-called gauge terms. They are a bit nasty, and I will mention them only here and not discuss them. But this is the two vector potentials that come from the magnet and from the nuclear magnetic dipoles. Okay, now let us think about which magnetic properties we would require. Well, for example, susceptibility. And magnetic interactions are pretty weak. For all practical purposes, susceptibility is a linear response. So you have your substance in a magnetic field. That is a matrix called the susceptibility tensor, and it gets magnetized in a way that is proportional to the local applied magnetic field. This matrix may tilt it somewhat, and so the magnetic moment is not necessarily strictly collinear to that magnetic field, but this is of the order of 10 to the minus fifth, so not strong at all. And then this induced magnetic moment will acquire an energy in our applied magnetic field, and so this is the energy of our magnetized substance, the extra energy that it acquires when it's been magnetized, and that goes back to Faraday. And then, if we take this and substitute it into this equation here, we get the extra energy. You can see it's quadratic in the applied magnetic field. And we can differentiate this. If we want the expression for this, we want the second derivative of energy with respect to this field and that field there. This has components x, y, z, that has components x, y, z. So second derivative of the energy will be d2e by dbx, 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 dby, dbx, dbz, and so on, 9 components in total. So this is a 3 by 3 matrix. So when you differentiate a scalar with respect to a vector twice, you get a 3 by 3 matrix. It's a kind of shorthand from the vector calculus. You could write it in component notation as well. So our susceptibility, therefore, is the second derivative of the total energy with respect to the applied magnetic field. If you look at those chemical shifts, they are exactly the same thing. You've got the energy of a nuclear magnetic dipole in the external field, and instead of the unit matrix in here, you have a unit matrix with a slight correction, which the chemists have called chemical shielding. And once again, if we want to know the content of this bracket, we need to differentiate the energy with respect to this and with respect to this. So chemical shielding here is the second derivative of the energy with respect to nuclear magnetic moment and the applied magnetic field. Notice that chemical shielding and chemical shift are somewhat different. Chemical shielding is literally the screening of the nucleus by electronic structure relative to bare nucleus in vacuum. Chemical shift is what chemists historically have been tabulating in their books, that is chemical shielding relative to their standard substances, like tetramethylsilane. So shielding is the absolute shielding, what the physicists would use. Shift is a difference between the shielding of the standard substance and the shielding of the substance that chemists are studying. So there's a minus sign and a reference shift in there, because to chemists it is convenient to measure those frequencies relative to something they just add to their sample that's just sitting there and not reacting. So be careful with this. Okay, but notice what we have here. We have second derivatives of the total molecular energy with respect to things. And now we need to work out how to differentiate molecular energies with respect to things. And now chemists, just, brace yourselves, fasten your seat belts. This is how you do those energies. right? D energy by D parameter is, well, the derivative with respect to some parameter of literally the energy, right? So the energy of the nth level in a system is the wave function of that energy level expectation value of the Hamiltonian. Remember the product rule when you differentiate a product, in this case a triple product. It's a derivative of the first term times the other two here, derivative of the second term times the other two there, derivative of the third term times the other two there. So this is literally just the product rule, and it does apply to non-commutative cases like what we have here. So what we need here is this derivative, and that derivative. Well, let's massage this a little bit. We know what h psi is, right? This is the eigenvector of h, so h psi is e psi, remember Schrödinger's equation. So we can use that. We can use that here also. H psi n will give us the energy again. So what we have, this energy here, and then derivative of psi, energy there, psi derivative of psi. But that's again a product rule. We can take energy out of the bracket, and that's the derivative of psi. But that's just a normalization condition. This is equal to 1, a constant. Derivative of a constant is a 0, so this term disappears. And we are only left with this. And Hamiltonian is quite easy to differentiate with respect to the parameters because we know the expression for the Hamiltonian, so it can be differentiated. So d energy by d parameter of the system is the expectation value of the derivative of the Hamiltonian with respect to that parameter. Hellman-Feynman theorem. Really precious thing in quantum theory because it is so cheap. Essentially, you just differentiate your Hamiltonian. It usually becomes simpler as a result because everything that doesn't depend on this parameter disappears, and you just take the expectation value. But this is only the first derivative. Remember, we needed second derivatives in the previous slide. I will not drag you through a very nasty derivation for the second derivative, but that is the expression. So second derivative of the energy with respect to two parameters is the expectation value for the second derivative of the Hamiltonian plus this monster sum over all of the excited states of the expectation values of the first derivatives, and notice here different indices divided by the excitation energies. Note how similar this is to perturbation theory. Right? Those of you who did second order perturbation theory will sort of vaguely recognize the expression. This isn't actually perturbation theory. This expression is exact. Okay, and so now what we need is these derivatives, and let's take a look at what those are. Well, we did, like we did a few slides ago, momentum becomes the momentum corrected for the presence of the Lorentz force. We know the sources of the vector potential, external field, and the dipoles of the nuclei. We plug that into Schrödinger's equation. Software would do this for us these days. We calculate the energies of the ground and the excited states, and then we take an expansion of that energy in the parameters we are dealing with. And remember, magnetic interactions are really weak, so this Taylor series actually converges pretty much at the second order. So we've got the terms here, just the magnetic moments. We've got the terms here, just the magnetic field. We've got the terms which have interactions of the magnetic field with magnetic moments. So this is the chemical shielding. And then these are interactions between the nuclear spins. So these are J couplings, for those of you who have done magnetic resonance already. Okay, and then we use Hellman-Feynman theorem to second order to get those derivatives, and none of this needs to be done by hand anymore. There are standard software packages, they have existed for many years, that would literally just do it for you. Click a mouse a few times, specify your molecule, click minimize the energy to get the equilibrium geometry of that molecule, and then click calculate chemical shielding. poof, a few minutes later you would have the chemical shifts and the J couplings if you want to, although J couplings are slightly more expensive. So this is the same method as any second order response property in electronic structure theory. If you're calculating vibrational spectra, this is how you would calculate the displacement derivatives. If you are calculating polarizabilities, this is how you would calculate electric field response derivatives, etc. Every kind of response property in quantum mechanics, in molecular quantum mechanics, is calculated like this. And that includes, as you can see, magnetic properties. So our magnetic susceptibility, now we know how to calculate this. At least we know which buttons to press and vaguely what the software is going to do for you. We insert appropriate derivatives of the Hamiltonian, and here they are. I've just calculated them here. Look into the literature, or in fact chapter 3 of my book, for the detailed derivations of all of that. And susceptibility has two terms. One is coming from the ground states, the so-called Langevin susceptibility, and one is coming from the orbital Zeeman interaction summed over all of the excitations, the so-called Van Vleck susceptibility. And typically susceptibility is caused by ring currents in the electronic structure, and this is hexabenzocarenine, and you can see the vector map of ring currents in the electronic structure that are introduced by a perpendicular magnetic field in this molecule. So conductor-like screening in this case. For the chemical shielding, likewise, Norman Ramsey, the guy who worked it out, got a Nobel Prize for that. These days, with artificial intelligence, you can make him smile. And this is literally the same thing, right? Second derivative with respect to magnetic moment and the magnetic field. Then first derivatives with respect to those individually. The unfortunate historical names for these terms, I think it was Ramsey that called them diamagnetic and paramagnetic. This has nothing to do with dia and paramagnetism. These labels are really quite unfortunate, but you will see them in the literature. But this is ground state, and this is sum over excitations, and these are all of the individual derivatives. So the ground term here is just electronic density modified with this distance operator, but the excited states have orbital Zeeman and spin orbit type terms, and you can see that you need to account for special relativity, particularly for heavy elements here, to get that correct. Thank goodness the software will do all of this for you. You just need to vaguely recognize the physical meaning of all of these terms in practice. Okay, so this is electronic structure theory. This is where magnetic interactions are coming from, and this is how software would calculate them for you if you ask. This is how an NMR facility looks. If you walk into our NMR facility here at Weizmann Institute, you would see more or less this. So giant, expensive superconducting magnets. You would have an overall hull. This is what you see there. Underneath the hull is vacuum chamber, and then a layer of liquid nitrogen to provide outside cooling and screening from the room temperature. Then another vacuum chamber and liquid helium. This is done this way because liquid helium is a lot more expensive than liquid nitrogen. You don't want to boil it off too quickly. So there are two layers of cryogenic voids in there, and then the superconducting magnet is immersed in liquid helium, and in the center of this magnet there are coils of the probe, which is inserted from the outside, and that's connected to the instrument electronics. If you look very, very closely inside this probe, this is about 5 millimeters across by 2 centimeters. That's the typical 5 millimeter magnetic resonance tube, positioned inside these electromagnetic coils, which are responsible for transmitting radio frequency magnetic fields that then, as we will see later in this course, manipulate our spins. Any serious chemistry department would have at least half a dozen of these. sometimes at lower fields, sometimes at higher. Biologists prefer higher field, material chemists prefer higher field, but to pharmacologists, in a lot of cases, particularly if you're having aromatic fluorine substituents, lower field is actually a bit better for various reasons that we will discuss later. MRI instrument is a scaled up version of that, again a superconducting magnet but with a much wider bore into which you can put a patient. The coils are proportionally bigger. There are additional coils because you need to make this magnetic field non-uniform to get location dependent magnetic resonance to get your image. Well, 7 Tesla MRI instrument is a dangerous beast. This is a nurse trying to roll a ferromagnetic trolley past a magnet with a predictable result. So what you do need then is to de-energize the entire thing, pull the trolley out or pull this ferromagnetic bed out. You know, there are airport style security gates at the entrance to MRI facilities, because if God forbid you have a piercing somewhere in your body, it will be torn out. So yeah, one has to check very carefully for ferromagnetic substances in this case. And MRI data is, of course, you are mapping magnetic properties in spatially selective way. This is a full body MRI scan, very, very expensive because those magnets, they begin again at 10 million pounds. Functional MRI, because blood is magnetic because of iron in it. If you've got local vessel dilation, you get more blood flow through there. You can spot it with magnetic resonance imaging. You can spot diffusion processes and do fiber tracking through your brain. If there's damage somewhere, diffusion processes are disrupted. You can have physiological information. You can see somebody's slipped disc that is apparently very painful here, MRI of spine. You can literally inject a gadolinium substance into somebody's bloodstream, which radically changes the magnetic properties of the blood, and then you can do angiography and see the cardiovascular system. This is diffusion weighted image of a stroke. If you have a stroke, blood enters the brain and you can see a change in magnetic properties. And then MRI of a tumor here. Again, gross abnormalities in physiology change the local magnetic properties of the tissue and you can spot it. And this is the current state of the art in there. In fact, the MRI facility here at the Institute is one of the best in the world. Functional MRI, I've already mentioned that because of iron and because of the fact that the magnetic properties of hemoglobin, which is bound to oxygen and not bound to oxygen, are very different. Tissue changes magnetic properties very significantly depending on whether oxygen is consumed and on the extent of the blood flow. So this is functional MRI. You roll, Mr. Simpson into an MRI instrument and get him to think about donuts. What will happen locally is oxygen will be consumed by the part of his brain that's responsible for donut perception, with the result that the local blood vessels will be dilated, the local blood flow will be increased, the local magnetic properties will change, and then you do the anatomical image, and then you do the functional image, you overlay it, and you know exactly which part of his brain is responsible for thinking about donuts. And this is currently a hot topic because, well, it's not quite reading thoughts yet, but at least you know which part of the brain is responsible for what. Industry is huge. For NMR alone, if you look at the forecasts, and these forecasts I think have been exceeded, we are talking billions of dollars worldwide in annual revenue because every serious pharmaceutical company would need one. Likewise, for the MRI, every serious hospital would need one. If you look at NMR statistics worldwide, there are tens of thousands of instruments at research organizations and industrial companies. Market capitalization of the vendors are in the billions, and there are tens of thousands of publications that are coming out per year. Similar for MRI statistics, except the market capitalization of the vendors exceeds the GDP of most countries. This is because of Siemens, General Electric, and other giant transnational corporations whose total turnovers are in the trillions of dollars. And again, the publications are in the tens of thousands. Of course, spin processes are ubiquitous. Photosynthesis, for example, involves spin-correlated radical pairs. Birds use a spin-selective photochemical reaction for navigation, and spin is at the core of every magnetic technology, from magnetic data recording all the way to spintronics these days. So, and of course, as I've already mentioned, every major chemistry department has at least 5 of these. So that's the overview and the basic physics of what is going on. And from the next lecture, we switch to the chalkboard and go into the nitty-gritty of how you analyze spin dynamics, how you model it, how you predict what's going to happen, and how you design and interpret magnetic resonance experiments in practice.